In this video, we're going to look at the behavior of our meters, our voltmeter and our ammeter, look at how they're kind of like switches and wires and that kind of stuff in a certain respect. And we'll talk a little bit about the internal resistance of batteries, because batteries, like every other circuit element, does actually have some resistance. Specifically, the connection of meters, I want to look over that. We've been playing around with that with a little bit in the lab, but because most of you haven't been actually connecting circuits, you may not have encountered kind of one of the oddities that happens when you don't have your meter in the right mode. We'll talk about how even when there are open switches or meters connected, you can still often find a voltage difference, which again, because we haven't been doing as much color coding by hand, may not be as obvious a thing. And then we'll look at the internal resistance of the battery, how that behavior goes. So I wanted to start with this. If you look at this, and you're going to be answering some questions as we go along, which of these meters are connected incorrectly? So I'm going to start there and have you indicate which of those are connected incorrectly. So the big idea here is that we know that ammeters are supposed to be connected in series with what they're measuring, and voltmeters are supposed to be connected in parallel. And here for A1 and V1, those are the opposite, right? The voltmeter is in series and the ammeter is in parallel. And there's a problem with that, and that's one of the things we want to look at. So what we actually do, right? Ammeters in series, their resistance must be, and this is a thing that we haven't talked about yet, if you're connecting an ammeter in series, what must be true about its resistance so as to not affect the circuit? That's right, it has to be low resistance. An ideal ammeter has no resistance, so it's just like an ideal wire there. It doesn't actually affect the circuit it's in. Voltmeters, we connect in parallel, and that must mean they have what kind of resistance, high or low? They must have high resistance, because otherwise that would be a short circuit that the electricity could flow through, the current could flow through with no resistance bypassing that resistor. And so that's kind of the key thing about how resistors behave. So ideal meters, right? Ideal ammeters have zero resistance, so they don't change the current in a branch. And ideal voltmeters have infinite resistance, so they don't change the voltage drop across that resistor. Now, this is, of course, impossible. It's impossible to have zero resistance or infinite resistance, but you can set things up where they have very small amounts of resistance. And this is one of the reasons, if you have a physical multimeter, there's not just one setting for voltage and one for current. There are different ranges of voltage, because depending on how big the voltage is, you can get away with different amounts of resistance, or depending on how much the current is, without really affecting things too much. So when we talk about voltages in a circuit, another thing we could think about is what would happen if I open and close this switch? So this is points A and B in my circuit. So if I'm just here and I have set up this circuit and the switch is open, what would the voltage be across A to B? 10 volts, 5 volts, or 0 volts? If you weren't quite sure, right, I would hope that you color code it and then use the loop rule. So if we color code this circuit, we have red coming from the positive terminal of the battery until we hit the 5 ohm resistor, and blue going to the bottom 5 ohm resistor. That means we could use any other color. I've used green here, but it could be green or yellow. Notice that the 5 ohm resistor that's green, I've actually color coded it. Normally we don't color code resistors, but you'll notice that there's no way for current to flow through that. And that is because the branch is not connected. So if there's no current flowing through it, it doesn't have a voltage drop. So the voltage or the color is the same on both sides, which means B is basically connected to the green part of the circuit, and A is connected to the blue. And green to blue, if we look down to the bottom resistor, is, as we go around our loop, right? 10 volts minus 5 volts equals 0 volts. Minus one more, and that gives us 5 volts as the missing piece. Right? Green to blue has to be 5 volts. Hopefully that makes a little bit of sense. What about here? What's voltage AB? This is a multi-loop circuit. This is an interesting one. It's actually much easier to do a multi-loop circuit with the, or multi-EMF circuit with the voltage disconnected, because no current will be running through that branch, right? In the middle branch, what is the current? That's right, it's 0 amps. So in the big loop outside, what is the current? 2 amps, exactly, because the REQ is 30 ohms, 60 volts. And so if that's true, we can say there's 2 amps running around that outside loop. And so we can figure out, using the loop rule, the left loop, 60 minus 20 minus 0 plus 10 plus VAB minus 0 minus 20, right, equals 0. So we've got a lot of terms there. We've got the 60 volt battery, the 10 ohm resistor, another 10 ohm resistor, a 10 volt battery, another 10 ohm resistor, the AB voltage, and then the final 10 ohm resistor. Right? As you go through, the missing piece is 30 volts, which would make the loop rule true. Another one here, what's voltage AB? What's voltage CD? So we'll start with voltage AB, right? We can do our lower loop. REQ is 25. Current is 3 amps, right? Notice there's no current flowing through the top. So we can figure out that if that's 3 amps, right, we get 75 volts minus VAB, right? Then that's minus 30 for the 10 ohm resistor equals 0. It's 45 volts. And you might ask, well, why would I bother doing that? Well, couldn't I just figure out the equivalent resistance, figure out the current, then figure out the missing pieces? Sure. But this is showing that we can use some of these techniques to get through this a little bit faster. And once we know voltage A to B, right, we can do a little bit more, right? Around the big loop, which you can't really see here, there's 0 amps up top, right? If we go around the big outside loop, we have 75 volts minus voltage CD, minus 20, because we're going the wrong way around it. There's 0 volts across the top 10 ohm, and then we already know there's 30 across the bottom, and the missing answer is 25 volts. Another question for you, identical resistors here, current through the ammeter. What is it? What is it? Remembering that an ammeter, right, is basically zero resistance. Zero resistance. So if we think about this, if there's zero resistance, essentially the color coding, right, would be the same color all across A to B inside of that. So we've basically got 2 resistors in parallel, then they connect back together with that ammeter, then 2 more resistors in parallel. So we have R over 2 plus R over 2 for a total resistance of R, right? Each of those branches has half of the current, right? And the current through the ammeter has to be 0 because there's 0 voltage in that segment. Here we got a couple identical bulbs. When the switch is closed, what will happen? It's a 12 volt right now, right? Going in and another 12 volt going in a big loop. What will happen when we close the circuit? Nothing changes, because if you look at what happens, the loops that you can do, the top 12 volt and bulb A will still have 12 volts across it. Bulb B will have 12 volts across it. In the original case with the switch open, it's 24 volts. Then each of them get half in series. But if you close it, they're basically in a parallel configuration with one battery. So they are all the same. So I'm going to do a quick demonstration here. This is now getting into our kind of last idea, the idea of internal resistance. So I'm going to build a circuit where the battery is no longer ideal. And we're going to measure the voltage of the battery with nothing connected, with the switch open, and with the switch closed, and see what they look like. So in this circuit, which is the one that we showed, we have a battery, which is a 9-volt battery here. We have a 10 ohm resistor. We have a switch, and we've got some wires. The only real change that I've made is I've put the battery resistance to something. Unlike an ideal battery, this is a real battery in simulation, so it should have some internal resistance to it. So I'll start by measuring the voltage, 9 volts, when nothing is connected. And that makes sense, right? It's a 9-volt battery. But watch what happens when I flip the switch. The voltage drops to 7.5 volts. Something interesting is happening there. I disconnect it, it's 9 volts. I reconnect it, it's 7.5 volts. So this kind of investigation is what we want to think about. Why would this happen? So we just did this simulation, and in our simulation, we saw that when the 9-volt battery, the rated 9-volt battery, was not connected, or at least the switch was disconnected, we got 9 volts. And that when we ran it attached to a light bulb, we got 7.5 volts. So why did the voltage of the battery decrease? Well, the difference is really because of what we call internal resistance, which we usually give a symbol of a lowercase r with the under subscript internal or INT. Real batteries are made up of physical material, right? They're not some magical thing that provides us with a voltage. They are something that actually has a chemical reaction, and electrons and charged particles have to move through physical space, and they have some internal resistance. And so this is how we tend to think of a real battery. An internal resistance, a little resistor that's stuck inside of this dotted line inside the battery, and an EMF, an ideal voltage. So normally, up till now, we've been thinking of all batteries as just being ideal voltages. But the reality is there's a voltage plus some internal resistance. Sometimes you also see it like this, although I tend to draw it in the EMF resistance with the dotted line around it. But this kind of shows that it's inside of the battery. Now, if there's an ideal EMF in series with a resistance, what's happening, right? Here's a circuit. This is a more representative circuit of what's actually going on inside of that. You have the EMF and the internal resistance, but you can't take that out. So when you measure the voltage of the battery, you're actually measuring what we call the terminal potential difference, the voltage from one side of the battery to the other, which has to include what's ever going on with the internal resistance. We know that the voltage drop, right, across this is just the voltage or voltage gain, across A to B is just equal to the EMF when no current is flowing. But when you let current flow, well, this is a different voltage because there's going to be a voltage drop across the internal resistor because current is flowing through it. And so that current times the internal resistance is going to be subtracted from the EMF, and that's what you will get. And so the consequence of this is the more current flows, the smaller the voltage of the battery is on the outside, the terminal potential difference, which is kind of an interesting result. So if the current increases, does the terminal voltage increase, decrease, or remain the same? And by terminal voltage, I mean C to D. It does indeed decrease because if we do the loop rule, right, normally starting with the battery, but if we start at the EMF this time, we go up some EMF, then we go around and drop for the light bulb, but we still have more to drop, so we're not back to zero until we get past the internal resistance. So how do these two things compare when we've got, say, 2 light bulbs or 1 light bulb? Well, the thing to pay attention to is that when there's 2 light bulbs in series or in parallel, as this is, the total resistance of the circuit goes down, the current goes up, meaning there's going to be a bigger drop across that internal resistance than there would be with just 1 light bulb. And if you have either of these situations where current is flowing, this will be smaller voltage measured across the terminals than the EMF. Right? As current goes up, current times internal resistance goes up, and so you end up with a smaller terminal voltage. So this is some of the stuff that's going on. And again, for those of you who've played around with the circuit kits in lab, you most certainly found this to be true, in class at school, that the batteries are labeled as 1.5 volts, the little C or D cell batteries, the circular ones, and the 9-volt battery, it's in its name, it's supposed to be about 9 volts. But as the chemical reaction goes through, eventually we say batteries die, right? Of course, they're not alive, so they don't die, but they just stop being able to produce via that chemical reaction the voltage or the potential difference that we expect. And so as that chemical reaction becomes less efficient or starts to break down, actually the resistance of them goes up over time, which is kind of interesting. And just like every other resistor, it behaves that the voltage across it is bigger, the bigger the current. The thing is, though, we can't measure it directly. So all we have is the ability to measure, say, current in a circuit, measure the terminal voltage, and we could do something like, measure current, measure terminal voltage, try to kind of plot them relative to each other and see if we could determine from that the EMF and the R internal. So it is possible to do. It just isn't something you can measure directly. So for example, right here we've got a circuit. I've got 3 10 ohm resistors. An ammeter is reading 1.66 amps. All right, my EMF is 30 volts. What's my R internal? So the way you have to go about this is say, well, the EMF is equal, as always, to I times the equivalent resistance of the whole circuit. But of course, the equivalent resistance of the whole circuit includes the internal resistance. So that 18 ohms that we get is R internal plus the 10 ohms in series with the battery plus the 5 ohm REQ from the parallel section. And that should be equal to 18 ohms. That's 15 external ohms, meaning we can get down to our internal by subtracting from 18 those 15, and you get 3 ohms. 3 ohms of internal resistance. So there's a bunch of stuff in this, but I think that the highlights are that zero resistance is what we have for an ideal ammeter. It just acts like a wire. Voltmeters have infinite resistance, in which case they act just like an open switch, which you can have a voltage across but no current flowing through. A closed switch just behaves like a wire, so we don't worry about that. And even batteries have resistance. And to find that resistance, you need to look at what's happening in the rest of the circuit in order to kind of work backwards and calculate what's going on in there.